Prime numbers are very useful in advanced mathematics. This is because every number greater than 1 can be written as a product of prime numbers. This is called prime factorization and will be the focus of this video. For our first example, we'll find the prime factorization of the number 54. The first step is to think of some factors that you know of the number 54. For example, 6 times 9 are equal to 54. We're going to make what we call a factor tree. So we're going to draw two branches, and we're going to put the factors that multiply to give us 54 at the end of each branch. Now, what you do next is you look at the end of the branches. If this number is a prime number, you're done with that branch. But 6 is not a prime number. It can, in fact, be factored again. And so we draw two more branches. 2 times 3 is equal to 6. Now, since 2 is a prime number, we're going to circle it because we're done with that branch. And since 3 is also a prime number, we're going to circle it. 9, on the other hand, can be factored further into 3 and 3, both of which are prime numbers, so we can circle them. At this point, the end of every branch is circled, showing that we have gotten down to all prime numbers, and so we can write our prime factorization as 54 equals 2 times 3 times 3 times 3. Since we understand exponents, we can write this as 2 times 3 to the third power, or 2 times 3 cubed. 6 times 9 are not the only factors of 54. 54 is an even number, so based on the rules of divisibility, we know that 54 is divisible by 2, and it's actually 2 times 27. We didn't have to start our factor tree with 6 times 9. We could have started with 2 times 27. Now, if we do this, we look at the end of this first branch, and we already have a prime number of 2. So we're going to go ahead and circle that. We look at the next one. 27 is not prime. 27 has factors of 3 and 9. Since the 3 is a prime number, we can go ahead and circle it. The 9, of course, is not a prime number because it factors into 3 and 3. Each of those are prime numbers, and so we circle them. And you'll see that it doesn't matter that we started with different factors. We still get 2 times 3 times 3 times 3, or 2 times 3 cubed. Let's work another example. We'll find the prime factorization of 450. Again, we'll do it two different ways just to see that we get the same answer. When I try to find factors of 450, I notice that it ends in a 0, so it's divisible by 10. And so I can start with 10 and 45 as my first factors. 10 factors into 2 and 5, both of which are prime, so I'm going to circle them. 45 factors into 5 and 9. 5 is prime, but 9 will actually factor again into 3 and 3. And so I get the prime factorization to be 2 times 5 squared times 3 squared. Now let's look at a different way to do it. Instead of starting with 10 and 45, I could have started with 2 and 225, in which case I would have circled the 2 because that is a prime number. Now, because 225 ends with a 5, I know that 5 will divide into it. 5 goes into 100 20 times, so it goes into 200 40 times, plus that extra 25, that's 5 more times, so it's going to be 5 times 45. 45, I can circle the 5. 45 becomes 5 times 9, and then 9 is 3 times 3. And you'll see that I get the same answer. 2 times 5 squared times 3 squared. It doesn't matter which factors of 450 you start with, you get the same result. That is always true when you work these problems.